All right, so today we're talking about normal distributions. This is the start of our new statistics unit, and please be patient with the length of the video today because this was all introduced in class. So we're going to be using mean and standard deviation of a data set to fit into what we call a normal distribution and to help us estimate some percentages. You're going to be able to recognize that there's data sets which do not fit into a normal distribution, so this procedure wouldn't be appropriate. And we're going to be able to use calculator spreadsheets and tables to estimate areas under a normal curve. So we're going to start off with a vocabulary review today. The first word we're going to go over is mean. You guys know it as average, of course. We're going to clarify that mean is the mathematical middle. It is a measure of center in a set of numerical data, but mean is not always the best indicator of middle of a data set. If you have outliers, it can really affect your mean. Outliers do not affect median, but they do affect mean. But mean is kind of a big topic when we're talking about normal distribution. One thing that you don't know about mean, the Greek word, I'm assuming, for mean is mu. So you will hear mean called mu. Here's the symbol for mu. And on a graphing calculator, sometimes you'll see it as an X with a line over the top. So kind of keep that in mind. There's other words for mean besides average. The median, of course, is where you line up all of the numbers and find the very middle one. Median, we're going to call that the actual middle because 50% of our data is greater than the median and 50% of our data is less. So median is the actual physical middle. Let's hurry and review what an interval is. That's going to be important. An interval is a set of values between a lower bound and an upper bound. So when you did intervals before, sometimes they would look like points. When I use the round brackets, you kind of have to use the context of the problem to know whether you're talking about a point or an interval. The round brackets mean everything in between -2 and 3, everything in between the two boundary points, but not -2 or +3. Like 2.999 would be part of this set, but 3 is not. So everything in between, but not the two ends. When you use square brackets, on the other hand, it means everything in between, including the two endpoints. So in this one, everything in between 4 and 10 are included, but so is 4 and 10. An outlier, we already know what an outlier is. It's a value far above or below other values of a data set. Remember that outliers can drastically affect mean, but they can affect median. So now we're on to new vocabulary. Our first new vocabulary for the unit is continuous data. Continuous data, the definition is a little confusing. It's a set of values for which there's at least one value in between any other two given values. So the best way that I can kind of describe this is think about when you get into a car. You turn on the car and you put it in gear and you press on the gas pedal. You are not instantly going 80 miles per hour, right? You have to accelerate. You have to go through a progression of speeds to get up to the speed you want to go. So sometimes that goes by so fast that sometimes we don't realize it's there, but you have to go 1 mile an hour and 2 miles an hour and 3 miles an hour and everything in between to get to, say, even 30 miles an hour. So it's a slow progression of numbers. Another thing, another example of continuous data is your age. You're not born one day and the next day you're 50 and the next day you're 12 and the next day you're 45 and the next day you're 18. you have to go through a progression, a natural progression of ages. You have to be 1, then 2, then 3, then 4, then 5, and so on. So continuous data, some examples are acceleration and deceleration, your age, your weight, your height, and like the temperature outside. Those are all good examples of continuous data. Data that does not jump around. The opposite of continuous data is discrete data. Now these are values with big gaps in between. If you think about when you're at the mall and you're watching people who are going the other direction, you're not guaranteed to see a 1-year-old, then a 2-year-old, then a 3-year-old. You might see someone who's 20, and then someone who's 30, and then a group of girls who are 16. And then you might see someone who's 12, and then you might see someone who's 50, right? So that's a good example of discrete data. You're not guaranteed to have any order to the numbers. Discrete data can also be things that are not numerical, like eye color. So here are some examples of discrete data. Counts, ranks, eye colors, favorite foods and names. So things that can jump around or things that are not numerical. So now, normal distribution. Normal distribution is a set of values that are continuous. So I have to have continuous data. I'm going to have data that's symmetric to a mean. Remember, symmetry means that both sides are a mirror image of each other. And I'm going to have higher frequencies when I'm close to the mean, right? More data when I'm close to the mean, and less data when I'm less data as I get further away from the mean. So let's take a look. With normal distribution, what all of this comes out to say is that I have a shape representing a normal curve. A normal curve is a symmetrical curve that represents the normal distribution. I need you to write this shape, to draw this shape in your notes, including the numbers below. There's big significance in the numbers that are below the normal curve. We're going to skip the samples of normal curves since I don't have the copyright for the video. So if you need some extra examples, come see me. So now let's go over the properties of a normal curve. So now that you have this picture in your notes, let's go over what it all means. So in the middle of a normal curve, you have the mean, otherwise known as mu, but you also have the median. So when I have normally distributed data, my mean and my median are one and the same. They're both going to be a fantastic indicator of middle. And then as I go to the right, I'm going to start adding standard deviations. Standard deviation is a measure of spread. It kind of tells me how far spread out my data is. So standard deviation is a big part of normal distribution. I'm going to add 1, 2, 3 standard deviations to get to the end or nearly to the end of my normal curve. On the other, well, before I say that, you need to know that it's possible to have outliers that are beyond 3 standard deviations away from your mean. So if I include all of the possible outliers, then everything to the right of the mean or middle of my normal curve contains 50% of my data. It's important to realize that that 50% really does include any outliers that might lie on this side of my graph. As I go to the left, I take away 1, 2, and 3 standard deviations to get to nearly the end of my normal curve. Again, I'm it's possible for me to have outliers that go to the left of the normal curve. So if I want to include those outliers, then everything to the left or on the left side of my graph contains 50% of my data. So this is split into half and half. Within the standard deviations, there's 3 super important percentages that you need to know. In a normal curve or in normally distributed data, between -1 standard deviations and +1 or +1 standard deviations, I find 68% of my data. Now this is a rough estimate. It's not always exactly 68, but for our purposes today, we're going to say that's close enough. So we call this within 1 standard deviation away from the mean. Within 2 standard deviations, I find approximately 95% of my data. And within 3 standard deviations, I find 99.7% of my data. I cannot ever say for sure that I have 100% of my data under this curve because of the possibility of outliers. We have to give ourselves a little wiggle room, and statisticians give us 0.3% of wiggle room for outliers. This is actually called the 68, 95, 99.7 rule. Another name for it is empirical rule. This needs to go in your notes, and this is something you need to memorize. So let me show you a little bit about what we do with normal curve. So let's say that we have a temperature controlled room. So in this particular carefully controlled room, the temperatures are normally distributed throughout the day. They have a mean of 0 degrees Celsius and a standard deviation of 1 degree Celsius. So Shane's going to randomly select a time of day to enter the room, and we want to know the probability that the temperature is going to be between -1 degree and +1 degree Celsius. So with normal curve, you need to draw a picture. So we're going to draw a picture of a normal curve, and that's going to help us a great deal with finding our information and our probabilities. So remember, in the middle of a normal curve is our mean. And the information in the problem tell us that the mean is 0 degrees Celsius. In a normal curve, remember we have 1, 2, 3 standard deviations on either side. So from here to this point, I need to add 1 of my standard deviations. Since my standard deviation is only 1 degree Celsius, I'm adding 1 degree every time I move a tick mark to the right. So I'm going to have 1 degree Celsius, 2 degrees Celsius, and 3 degrees Celsius to the right. As I move to the left, every time I move 1 unit to the left, I'm subtracting 1 standard deviation. So I'm subtracting 1 degree Celsius. That's going to give me -1 degree, -2 degrees, and -3 degrees Celsius to the left. The question says, what's the probability that the temperatures are going to be between -1 degree and +1 degree Celsius? So I'm trying to find the probability of the temperature being in this portion of my normal curve. Now we know from the empirical rule that everything within that portion of the graph within 1 standard deviation is 68% of our data. That means that Shane, any time of day when he enters that room, has a 68% chance that the temperature is going to be between -1 degree and +1 degree Celsius. So now let's look at some college admission test scores. The scores of a particular college admission test are normally distributed. It's really important that you look for those words because you know then that you can use a normal curve. In our normal curve, we find that these test scores have a mean score of 30. So I'm going to put in the middle of my normal curve a 30. We also have a standard deviation of 2. So when I draw in my 1, 2, 3 standard deviations on either side, remember I'm adding 1 standard deviation. Standard deviation is 2, so that means every time I move 1 tick mark to the right, I'm adding 2 points. So I have 32, 34, and 36 on the right-hand side. As I go to the left, I'm taking away 1 standard deviation each time. So I get 28, 26, and 24. Now, my question is it possible for people to score less than 24 on a test? Sure. It's just because of the normal curve and the normal distribution, it's not very many people that will do that, but it's still possible. So keep in mind our outliers on either side. This tells us that Erin scored a 34 on her test. So Erin is right here. We want to know the percent of test takers whom Erin outperformed on the test. So in other words, we want to know what percent of people scored less than 34. So with this kind of problem, it's not straight up one of our 3% in empirical rule. So I'm going to break this up just a little bit. First of all, this middle line, this mean, is a natural break in my normal curve. So I'm going to break my data into 2 parts. I have the part to the right of the mean, and I have the part of my graph that's to the left of the mean. Okay, now people who scored less than Erin can also be the people who scored less than 24. That's going to be important to remember. So in my data, everything to the left of the mean, everything in blue, including all of my outliers, remember that's half of my data, or 50% of my data. It's the pink portion that's a little more challenging. Remember, I have 2 standard deviations to the right of the mean. And if I go from 2 standard deviations below to 2 standard deviations above, everything within this area was 95% of all our test takers. The pink portion is half of that 95% area on my normal curve. Half of 95% is 47.5%. So if I look at the entire shaded area, I have a 50% portion and a 47.5% portion. That's going to give me 97.5%. 97.5% of all the test takers scored less than Erin did. That's pretty phenomenal, right? But with this example, I need you to remember that there are times when you'll have to take one of your 3%, the 68, the 95, or even the 99.7, and be able to split it in half so that I can get a total probability percent. Now, one more thing There's also a type of data where all the data has the same probability of happening. Last year we talked about probability and we talked a lot about rolling dice. If I roll a single 6-sided die, the probabilities of rolling a 1, 2, 3, 4, 5, or even a 6 are all the same probability, right? I have the same chances of rolling a 2 as I do of rolling a 5. They're all 1/6. Well, this type of data is not normal distribution. This type of data is called uniform distribution, and it works a little differently. In uniform distribution, because everything has exactly the same probability, my graph looks more like a box than it does a bell curve. This is called uniform distribution because the data is spread uniformly throughout the distribution. And to find probabilities in uniform distribution, we're going to apply the probability fractions that we used last year. So let's say Madison needs to ride a shuttle bus to reach an airport terminal. The shuttle buses arrive every 15 minutes and the arrival times are uniformly distributed, which means that I need to use a uniform distribution or a box. We want to know the probability that Madison's going to need to wait for more than 6 minutes for the bus. So remember, the buses arrive anywhere from 0 to 15 minutes after someone arrives, right? So Madison has every chance of waiting from 0 to 15 minutes. So that's where we're going to draw our distribution. We're looking for the times that are greater than 6 minutes. Keep in mind that even 6.01 minutes is still considered greater or more than 6 minutes. So I'm going to shade in everything from 6 to 15. So as I find probability, I'm simply going to compare the width of the shaded area to the width of the whole box. The width of the shading, and it's easiest if you count the spaces or subtract the numbers, 15 minus 6 would work. The width of the shading is 9 units, and the width of the whole box, or the whole distribution, is 15. 9 over 15, when I change it to a decimal, is 0.6. This is the probability that we're going to use this unit, but sometimes we have to be able to change that to a percent. So 0.6, remember, is the same as 60%. Madison has a 60% chance of waiting more than 6 minutes for that shuttle bus. That's uniform distribution. Be careful when you're doing your assignment to look for the words normally distributed or uniformly distributed, because they will use different types of charts and different percentages. We'll talk later about data that is neither, because you can have data that doesn't fit under a normal curve or into a uniform distribution. That's all for today, guys. We did our assignment in the Unit 1 workbook. We did pages 17 and 18. Remember to come to Charger Time with any questions you have. I hope that you have a great day, and I'll see you next time.